Hello, everyone. Welcome to the third season webinar series on rate splitting multiple access in 2023. This webinar series is organized by IEEE ComSoc WTC Special Interest Group of RSMA. And I'm Lina Yijiemao from Shanghai Tech University. So this is the last webinar of this season, and it's our great honor today to have Dr. David Vargas from BBC Research and Development UK as our distinguished guest speaker. So first of all, please allow me to make a brief introduction of David. David received his PhD degree in telecommunications from the Technical University of Valencia, UPV, Spain in 2016. And from 2009 to 2015, he was a research engineer with the Institute of Telecommunications and Multimedia Applications of UPV. And since 2015, he has been with BBC R&D, where he is currently a lead research engineer. David has contributed to standards development organizations such as DVBA, TSC, and 3GPP, and he was a 3GPP Rank 1 featured lead on new radio multicast broadcast services work item for release 17, and he is currently chair of the content distribution, standards, and architectures working group at 5G MAC. This is a cross-industry association bringing together media and ICT industries collaborating on market-driven implementations for 5G. He has been a guest researcher with the Vienna University of Technology, Austria, and the McGill University, Canada. David and his co-authors received the IEEE Broadcast Technology Society Scott Held Memorial Award for the best paper published in the IEEE Transactions on Broadcasting in 2019. And his research interests include multi-antenna communications, signal processing for communications, and the wireless communications. So before David's talk, I would like to remind the rules of our webinar. During the 50-minute talk, please keep yourself muted and you can type your question in the chat box. And after the talk, we will have a 10-minute Q&A session. You can unmute yourself to raise questions directly, or I will choose 2 to 5 questions from the chat box. All right, so let me stop sharing.
Okay, thank you very much. Let me share. Okay, so you can see the right screen, right?
Yeah, I guess you need to switch to not the presentations. Yeah, perfect.
Okay, perfect. Okay, so well, thank you very much. It's my pleasure to be here. So well, today, today I'm going to present a bit of our work on practical developments for rate splitting multiple access, RSMA for 5G, and a bit of discussion about what next steps for 6G. So this presentation co-authors Professor Bruno Clerks and then Sibo Sang. So Sibo also has done a lot of the work on the implementation and the simulation results you will see later in the slides. So let me just 1 sec. Okay, yeah. Yeah. So this is the outline of the presentation. I wanted to start a bit from the top, like how do we think this from a high level requirements in the BBC, and then how we think about how technical solutions then can help us then meet some of those requirements. Then a lot of you will be familiar with with RSMA, but I will explain a bit the architecture, how it can meet different use cases, and why meeting use cases, I think, would be important. So it's a candidate technology for 3GPP technologies. Then we present a bit of work on receiver architecture, so beyond successive interference cancellation. And then I will show you our results we submitted to the recent 3GPP Release 19 workshop in June. Release 19 workshop that was held. It was to decide the next set of features for the next release of 5G Advanced. And I will conclude just with some thoughts about the timeline for the IMT 2030 framework, so 6G, and some conclusions. So these some high level requirements. We submitted some of these to the 3GPP Release 19 workshop, but just to give you a bit of introduction, like the digital first BBC strategy. So in the BBC, we are moving towards, have the aspiration to move in the future to a more internet-centric distribution approach. So we are already distributing content over the internet, but in the future, then we will have the internet will take a more prominent role in our distribution strategy. So once we are in this future that all our content was over the internet, then a lot of users will receive our content via mobile broadband networks. So users out of the home and on the move will be probably served by mobile broadband networks. So that's why we are interested on influencing and shaping 3GPP standards. So we know that those standards meet our requirements, and also we then try to maximize the quality of our services. That's the motivation why we get involved. And then a bit of requirements on a internet-only distribution approach. Then, so we have requirements, a public service broadcaster, we have universal access. Then we do care about quality. So quality of service. So we need to still rely on quality, reliability, and latency. And then we have our services. So live content is a really important service proposition for us. It's something that makes us distinctive. But we also need to deliver on demand and new forms of immersive experiences. For instance, XR, as they get more prominent, then we will also want to use these to increase to maximize the experience of our users. So regarding a bit of more technical enhancements to address these more high-level use cases, coverage. So we need coverage from all operators. So if we need to cover everyone, so it doesn't, if only one operator is covering one area, then we also need to cover other users that may have been served by other mobile network operators. Capacity. So we need to have capacity both in rural areas. Rural areas are very important for us, but also in high demand density areas. And I will explain a bit more later about that. Adoption is critical. So we want features in the standards. Let me remove this. So that are adopted, and this may seem quite obvious, but so for instance, if there are technologies in the specification that never really get adopted, then those are useful. If they increase a lot of they have a lot of complexity as well, there may be barriers for adoption. So features that have widespread support, they are in all devices. So you have a feature that is only on a subset of the devices, then you may not get the gains. So if the feature is in all the devices, then you will get all the benefits of the scale. And so we'll talk a bit more later as well about features that address multiple use cases and verticals. And then just a final thought, we also, in our thinking and design, we always have environmental sustainability as an important requirement. So a bit of discussion on the challenge in high demand density areas. So this is being discussed quite recently in the UK, but of course, I think this will be also similar in other areas, in other countries, other countries. So around 1% of the geographical areas being served by mobile network operators are classified as high demand density, and those areas actually drive estimated 20% of the total mobile traffic. So these are areas, right, like dense urban areas, airports, railways, subway station, major public events, where you have a lot of users and devices in the same place. But that's going to drive a lot of intensity in the network. So therefore, there is a lot of discussion in the industry how to address those challenges. And then this drives as well technological innovation. So I will explain later as well why we think rate splitting can play a role here. So then multi-user MIMO. So multi-user MIMO is a key technology for mobile broadband. It really made the difference between 4G and 5G. In 4G, there was already multi-user MIMO, I think, in the specs, but I think the mass deployment in 5G has made the difference on the spectral efficiency. So to support large number of users and high data rates. Regarding standardization, MIMO has always been one of the largest projects in 3GPP run since the start of new radio specifications. It also always have a lot of mobile network operator support. Because if you increase the capacity of with MIMO, you increase features in MIMO, increase capacity, that benefits a lot of users on the network. So, however, there are still challenges for multi-user MIMO, especially high demand density areas. So if you have a lot of users packed together, then the orthogonality of the channels may not be orthogonal anymore, then linear processing may lose some performance. Or when you have inaccurate channel state information on the transmitter, then you start to have more interference between users. And therefore, this is when we think maybe rate splitting can play a role as well. So now jumping into RSMA architecture and some of the use cases. So you may be familiar, but just so we are all in the same page, on the left, so here I'm discussing unicast only architecture. So on the left, we have a transmitter, and on the right, we have multiple users where we have a bit more detail for the user, the kth user. So we have k unicast messages going to the transmitter. So one message for each user. So we have one message for each of the k users. And then what we do is with each message, we split into a common message and into a private message. And then we take all the common messages, all the common parts, and we form a single common message, WC. So what we transmit, so now we have k+1 streams. So we have WC, so it's a common message that contains parts of all of the k unicast messages. And then we have the other k private streams. And then we precode, and then we transmit. And then at the receiver needs to decode both the common message and the private message. And from the common stream, it can subtract the adequate information to form the original, to have an estimate of the original unicast transmission. So the benefits of RSMA in high demand density areas. So here on the left, we have a diagram here, like multiple transmit antennas. We have two users, and on the left, those two users may be quite far apart. And then on the right, you can have those users are closer together. And that could be like something could happen in a high density demand area. So what we have now also the beams, the representation of the beams. So we have the private beams, and then we have also the common beam. And then we have the flexibility to design the power ratio between the common and the private. So here on the left, if the users are quite far apart, channels could be quite orthogonal. So then the power to the common stream we may put less power to the common stream. And in the extreme case, it may fall back even to multi-user MIMO SDMA architecture. But then on the right, if users are closer together, there may be more interference. Then we can put more power in the common stream to manage that inter-user interference. So it's a flexible scheme, and so you can design the powers accordingly to your scenario. So more simulations about that later. So now with the same architecture, so now we are discussing joint unicast and multicast. And this is quite, so you remember we have a common message. So we have a common pipe where for unicast only, we were transmitting parts of the unicast messages. So that naturally accommodates if we also need to transmit a multicast message. And here I mean, let's say we have a live program, a football match we need to transmit. So that common pipe will transmit the live program plus the unicast portions that would be used to manage interference. And then at the receiver side, once we do the decoding, we will have then both streams, the multicast stream for the live program, and then as well as the unicast for whatever other service the users may be enjoying. So with the same transceiver architecture, we could support different delivery modes. Unicast only, let's say we are just delivering on-demand content, or we have joint unicast multicast. So let's say we have live content plus personalization events. So there are other applications. I think previous speakers in this webinar series have discussed many of these aspects. So rate splitting can help, for instance, in satellite environments, integrated radar, sensing and communications, RIS, reconfigurable intelligence surfaces. So, and I think this is quite, as I mentioned before, a feature that can help you in different use cases, in different applications. I think that's an important feature for next generation wireless communication systems. So I'm building a bit on this. So why we think then RSMA is a candidate technology for 3GPP physical layer radio interface. So 5G is a general mobile broadband communication platform. So 4G was addressing internet connectivity to people. 5G has been conceived as, of course, we have as a key use case providing more connectivity and higher bit rates, but also addressing other industries, for instance, automotive, industrial, media industry. So it's a general platform with a set of common technologies that can be used for different scenarios. And I think that's a key type of design philosophy. For instance, just to put as an example, in 4G, 4G MBMS, so it was the multicast capability for 4G, was designed to only address TV applications. And that didn't really take off massively. In 5G, now you have 5G MBS, or multicast broadcast, and that was more conceived as a general point to multi-point communication. So it could address a public warning communication scenario, or a live event, or a automotive delivering a map to cars massively. So that was more, it got more traction. So RSMA unifies different multiple access technologies. I think a lot of the previous speakers as well touch on this. So orthogonal multiple access, OMA, SDMA, space division multiple access, and NOMA, non-orthogonal multiple access. And then here is a bit of it's a subtle point, but I think important. So, and as I mentioned, so RSMA can support different delivery modes. So you could have RSMA to deliver unicast only. That's probably the most relevant, well, most used use case in 5G, like a lot of the services use unicast. Then you could have multicast only, or you could have joint unicast multicast. So we see like, okay, you feed two birds with one stone. So you improve, let's say you deploy this for the improving unicast only, because that's your main interest. Then you have an architecture when if you need it, then you could also have multicast, because then you have the pipe there already. So if, for instance, for us, we are interested on live content delivery at scale, then that multicast capability would be there. So now we go a bit more, we jump a bit more into the different receiver architectures, so beyond successive interference cancellation. So a lot of research work, literature assumes successive interference cancellation as the main receiver architecture to decode the common and private messages in RSMA. There has been, there are papers, and as well, I wanted to point here that in industry forums, 3GPP and DVB, there has been studies about of different receiver architectures to manage interference. It may be between inter-user interferers or inter-service interference, different applications, but different architectures to manage interference. So we are reusing some of these architectures that have been studied in these forums, and then we show, then analyze how they perform with RSMA. Okay. So here, because you cannot see, let me just, well, let's see. So here we have, the first is 3 architectures for successive interference cancellation architectures. There are more details in the paper at the bottom of the page. So the first one is the classical ones who have hard code word level SIG, so hard quick. So here, first we decode on the top the common stream, and then after interference cancellation, we will decode the private stream. A bit more detail. So what we demodulate here at the beginning is just the marginal constellation of the common stream. So we assume the interference of the private stream is Gaussian noise. And then once we decode, we have the LLRs, we take a hard decision of the LLRs. So from LLRs, we pass to zeros and ones. So we reconstruct we re-encode, modulate, and subtract that interference from the main received signal. And then once we have this reduced interference stream, then we decode the private stream. So this is, excuse me, I think the classical architecture that is mainly considered. On the bottom of the right, we had a bit of discussion on complexity. So here, what we showed was a bit of demodulation complexity. So how many distances we need to calculate for the demodulation, and then additional buffer size. You need to store, for instance, in this case, we will need to store 1 code word for the processing, and then additional delays for processing, such as interleaving and mapping. So for the hard quick, we will do 2 marginal demappings. So the order of the complexity will be the distances we need to calculate for the constellation of the common stream, XC, and then the distances we need to calculate for the modulation of the private stream. So then we have the second architecture is soft code word level SIG, and this is an enhanced architecture compared to the hard. So here we are going to exploit the soft information from the LLRs. So here what we do is we do a maximum likelihood demapping, a joint demapping between the common and private stream. And then with those LLRs, we decode the common stream, and with those LLRs, that will give us the estimate of the common stream. But then those LLRs, that prior information can be reused. So when we demodulate the private stream, we can reuse the distances, but we update those LLRs with the prior information. So this is quite kind of like iterative remapping and decoding architecture. Then once with those updated LLRs, we can decode the private stream, and we will have our estimate of the private stream. So we will see later a bit more how this performs. So regarding complexity, here we do the joint demapping, the joint maximum likelihood detection. So here then the demapping complexity increases, then we will get better performance. We still need to store 1 code word in this processing. There will be additional delays for interleaving and mapping. Those details are hide here in the figure, but we will need to do those. And then the final architecture, SIG architecture, is soft code word level SIG2. So here, what we do is we do marginal demapping of the common stream, and we decode, and with the updated LLRs, then we can calculate the probability. So we can calculate an estimate of the transmitted symbol. So we can calculate the mean and the variance. We can do a soft symbol cancellation, and then with that cancel with the stream with the cancel interference, then we can perform a marginal demapping of the private stream and then decode. So this is an alternative architecture. So here regarding complexity, because we do 2 marginal demappings, the complexity would be lower than a joint demap, but we will still have the buffer size and additional delays for interleaving and mapping. So now two more architectures, non-SIG, so that they don't require SIG. So at the top, we have jointly mapping, and then at the bottom, soft symbol level interference cancellation. So the jointly mapping architecture, so this is a maximum likelihood detection, joint detection. So here we will jointly demodulate the common and private streams. And then the LLRs would directly, you will feed the appropriate LLRs directly to each of the branches for the common and then for the private stream. So here, the complexity, higher the modulation complexity because you need to do the jointly map. There is no buffer. We don't need to store a code word, and there is no reinterleaver and mapping. And then the last architecture, this is quite similar to the previous SoftQuick 2. So here, after the marginal demap, so first we demap to a marginal demapping of the common stream, and with those LLRs, we can do a soft symbol cancellation. So with those LLRs, we can calculate an estimate of, we can calculate the mean and the variance of the transmitted symbol, and we can softly cancel that. In the previous slide, this same architecture, we were taking the LLRs after the FEC encoding. So those would have better, because those would take the coding into account. But this one, the modulation complexity would still two marginal demappings, but there wouldn't be, we don't need to store the whole code word because you can do this as you modulate the different symbols, the different resource elements, and there wouldn't be any additional reinterleaving and mapping. So a bit now of simulation results. So we have done some link level simulations. So on the left, you have here the model. Excuse me. So here we have a non-line of sight model, and we have users. So this is a scatter of ring, a ring of scatters, and we have the users placed within the ring. Then if we make delta smaller, then these rings become smaller. So then users get closer together. So this is to model high density demand areas. Some parameters on the right. So we assume one transmitter with 4 antennas, 2 users, each with 1 antenna, perfect CSIT knowledge, polar codes as channel coding, but later we will show you results with LDPC. And then the precoder design, more details in the paper, but it's a maximum sum rate precoder. So here we show you link level simulation results of bit error rate against the SNR for the different architectures we discussed before. And then we have the common stream on the left and the private stream on the right. Modulation and coding rate for the common stream, QPSK rate 0.54, and the private stream, QPSK rate 0.3. So here we want to see, so we have designed the code rate and the constellation. We have selected the code rate, so the common stream and the private stream, they fall around the same SNR. It's a good operating point. So here what we can see is, well, the different architectures provide, they work. So that's a plus. There are some differences on performance. And in this scenario, so SoftQuick 1, so the architecture that really has soft cancellation provides the best performance. Then SoftQuick 2, HardQuick, jointly mapping, and SoftSlick. And now we wanted to show, what we want to show here is the impact on error propagation. So here what we have done is the private stream, the common stream, we have increased the code rate. So we put more errors. So we said, okay, at 10 dBs, we have quite high error rate. And let's see what is the impact on the private stream. So how these errors propagate. So you can see different architectures behave differently. HardQuick doesn't really, the private stream, those errors really affect the performance. And the same as SoftQuick number 2. Those are interference cancellation types of receivers. But then joint mapping, soft quick one, and soft slick, they really, those have actually, they are more resilient than this error propagation. So this is an important consideration to take into account. As well, the point we wanted to make is like, then there are different architectures, different trade-offs of complexity and performance, and then it's as well up to the companies implementing that they can choose depending on their application. So just the point we wanted to make is like, you don't need, you are not forced of using SIG if we want to decode RSMA. There are different architectures, including non-SIG. So now a bit of showing you our results that we submitted to 3GPP Release 19 workshop. So what we have used here is the 5GNR specifications. So we are evaluating the performance of the physical downlink shared channel, the PDSEH. And on the left, you have the generic transport processing chain. So we had to do some modifications to accommodate rate splitting that follows what we have discussed. So, we have the input to the transmitter is K transport blocks. So we have one transport block for each user. But then there's going to be a demultiplex. So each transport block is going to be demultiplex into a common block and into a private block. And then we take all the common blocks and form a common transport block. And then the rest of the K private blocks remain private transport blocks. So we have, as before, K+1 transport blocks that go through the general transport channel processing as defined in the 3GPP specifications. We will have CRC, LDPC coding, rate matching, scrambling, modulation, layer mapping. In these simulations, we didn't have multi-layer MIMO. We just had one layer. But if there would be multiple layers, then we'll also do multi-layer MIMO. And then we do multi-antenna pre-coding and resource mapping. And resource mapping means putting the information in the resource blocks in time frequency or VM location. So consider receiver architectures the same ones as before. Just as a reminder, the joint demapping is a joint demap. It's a maximum likelihood detection between the common and private streams. And I mentioned because we are using a similar architecture for SDMA. And these are the system parameters. So it's a lot of information here. So this I put, I'm not sure if you can see it because here I have my work bar, but there's here the reference for the paper we submitted to 3GPP. So we have chosen parameters to have a fair comparison between multi-user MIMO SDMA and then rate splitting. So carrier frequency 4 gigahertz, TDD, time division duplex, 20 megahertz bandwidth, and then I will mention a bit later more about the channel modeling. So we use the first slots for uplink, and then the rest of the 18 slots for downlink. And then we use the modulation reference signals. So just to be fair on resources, type 2 for the RSMA and type 1 for multi-user MIMO. 4 transmit antennas and 2 users, each with 1 antenna. And we have LDPC decode with 50 iterations. And then the modulation, I will explain a bit more later, but we have chosen modulation orders, so we have similar demodulation complexity. Decoder design is similar to the previous analysis, so maximum sum rate and details in the paper. So now we want to just a bit of detail of what is the baseline. So we compare against what is standardized. So 5GNR multi-user MIMO, also known as space division multiple access. So with we consider two types of receivers here. Single user detection, that's probably the standard detection. So you do marginal demapping, so you demap the desired signal, assuming the interference is Gaussian noise. Here the precoding is zero forcing. And the second architecture is joint demapping. So this is a joint maximum likelihood detection of the desired signal and the interference. So this is, as we have done for RSMA, the joint demapping of the common and private stream. Just to say, this is quite timely because this is a type of receiver architecture that is recommended by 3GPP-TR 38878. So there's a study, recent study on, it's a run for study on NR demodulation performance evolution. So in this study, they were studying advanced receiver structures to handle inter-user interference for multi-user MIMO. And the simulations were for two users, you have two users, and then you have interference between these two users in multi-user MIMO setup, and then advanced receivers to cope with that interference. There was also assuming you will have network assistance information, so the UEs need to know the modulation of the interferent UE. So after the study, one of the recommendations is to include a joint demapping type of receiver as an advanced receiver type, and also to specify required information and the modulation requirements. The specific type of receiver is called reduced complexity joint detection of useful interference and interference modulation symbols. But this is kind of like a sphere decoding type of demapping, but the performance would be a ML performance. So quite timely as well for our studies. Regarding precoder design, so here we use maximum ratio transmission or regularized zero forcing. So there is some potential interference that the receiver can actually demodulate. So the environment, so here we are using CDL, cluster delay line channels, as specified, but we were using using these realistic environments, and then with ray tracing analysis, you can derive the statistics that you can plug into the CDL. So we analyzed two cases. So here we have the antenna in a roof, and then we have users in a garden. The users can be in different locations. So case one is when two users are 20 meters apart, and then case two, when they are 40 meters apart. So the simulation results, so RSMA versus multi-user MIMO, and this is unicast only. So as you can see on the left, the scenarios when you have the two users with if blue dots 20 meters apart. So here, the target spectral efficiency is 3.4 bits per resource element. So here we have block error rate against SNR for user one and user two. And we have different RSMA with different types of receivers, as we discussed in the previous analysis, and then multi-user MIMO. So multi-user MIMO, zero forcing, QPSK, single user detection, multi-user MIMO, zero forcing, 16QAM, single user detection, and then multi-user MIMO, MRT, QPSK, joint demapping. So this would be jointly demapping the interference of the desired and the interference, and then multi-user MIMO, regularized zero forcing, QPSK, joint demapping. So there is a lot of results, but the point, well, as I said before, we have chosen the constellations. So when you do a joint demapping, so there is similar demodulation complexity. So we have QPSK for RSMA or QPSK 16.1 for multi-user MIMO. So from the results, you can see we have here all the RSMA for user one, and here, and then variety of performance for multi-user MIMO. But the key point is there were significant gains based on link level simulation for RSMA when these users are relatively close to each other. Now we are going to see what happens if we put the users, we space them, we increase the distance to 40 meters. So here, now distance is increased, and then you can see that actually the gain reduces. So channels become less correlated, and then the performance between rate splitting and multi-user MIMO then decreases. There is no loss. That is quite important as well to highlight, but the gain decreases. And then this is results for joint unicast and multicast. So here on the left, so we have again same simulation parameters as before. So we have, but we are also transmitting a multicast content, as I said, maybe live content, football match or whatever, and then plus some unicast. So here we compare RSMA against orthogonal unicast and multicast. So some of the resource, so part of the bandwidth will be used for multicast, part of the bandwidth for multicast or multicast unicast, and then non-orthogonal unicast multicast. So here we have the multicast and the unicast are superimposed. Just to say, like in RSMA, the common stream and the private streams are also superimposed, but the common stream has both the multicast content, live program, plus unicast messages to handle interference. Here we are only discussing case one when users are relatively close to each other. So here we see that RSMA provides higher spectral efficiency. So there is performance improvement compared to both orthogonal approach and then non-orthogonal approach. So yeah, I'm going to the end of my presentation. So ITU timelines and some conclusions. So ITU timelines for IMT 2030 and then potential opportunities. So on the right, you have the ITUR timeline for IMT 2030. So this is the framework to develop candidate technologies for IMT 2030. So what is, I think, will be known as 6G. I think the goal is to have maybe commercial services around early 2030s. And here there is from 2027, I think, is when the different standard developing organizations can send submissions. 3GPP very likely will also work towards a submission to the IMT 2030. So in the last plenary meeting, RAN 101, there were multiple contributions from multiple companies discussing, okay, we need to discuss the timeline for 6G. There hasn't been any agreement in 3GPP whatsoever, but there were most of the contributions were saying release 20, fair release to have studies on 6G, so requirements and technologies, while release 21, the first commercial 6G release. But as I said, this is not agreement. This was just our proposals from companies. What I wanted to show is the timeline on the left for the release. So this is taken from the website of 3GPP. So the timeline from 3GPP for release 19. And release 19 is going to finish around, it should start in January, this coming January, and it should finish around second half of 2025. So around second half of 2025, potentially 6G studies will be starting happening already in 3GPP. That is quite soon, if you think about it. So there could be opportunities as well for SMA, but will need to fit these timelines. And just to conclude my talk, so some key messages. So RSMA unifies many existing multiple access techniques, OMA, SDMA, and NOMA, enhances multi-user MIMO by achieving higher data rates under imperfect or perfect CSIT. one key point as well is the same architecture can support different delivery modes, unicast only and joint unicast multicast. And that's something we see has quite a lot of potential, especially to improve unicast, but also if we want to deliver live content at scale. We have done an analysis, and there are different receiver architectures that are possible for RSMA, including non-SIG receivers. And we have also shown the benefit of using RSMA against multi-user MIMO. As users get together, then this higher interference, potential higher interference, then RSMA can help there. And then also results, we have shown results for joint unicast and multicast, and these link level simulations based on 5G standards, so that have better performance as orthogonal, multicast unicast, and non-orthogonal unicast multicast. And just to conclude, as a thought, there's a lot of work, literature around RSMA. I think there could be a need a bit of pre-standardization activities on RSMA led by industry. This coming up, taking into account the upcoming standardization of 6G. So I think there is need to be a bit of industry consensus about RSMA. What are the benefits? What are the challenges? And to move this also the discussion with companies. I think there are also a lot of multiple companies discussing, but we need more discussion as well with other key players. So that concludes my presentation. Thank you.
Thank you, David, for a very interesting and comprehensive talk. So we have some questions in our chat box, and there are 2 questions from Sunda. The first question is it fair to say that SIG is a significant impediment to widespread RSMA acceptance in 3GPP? And the second question is the roadmap to acceptance of these SIG-free RX architectures in 3GPP?
So thanks for the question. So we had the feeling like the SIG has always been seen as it increases quite a lot of complexity. But when you start analyzing the complexity, you could also have joint map that will have more the modulation complexity, but that's also been recently standardized in 3GPP. So I think it's difficult to really, for instance, I'm not coming from a company of a chip maker, and then it's difficult to really know what do they believe is very complex or not. I think what we wanted to do here was put different type of receiver architectures on the table, and then it would be then maybe easier to have a discussion maybe with chip makers could say, well, actually this component takes a more impact in my design, so I would prefer after all SIG, or no, I would prefer as a joint map. So because it was very difficult to move the discussion as well forward, we decided to have this approach. But how complex would be in practice? I think is a difficult question. And regarding your second point, there have been studies in the past about considering SIG type approaches in 3GPP. I think the MUST study item considers SIG architectures. Those were studies. And a point as well is, even if an architecture is, I think what you standardize are the modulation requirements. Even if those are standardized, doesn't mean we'll be implementing in practice. I mean, having something in the standard doesn't mean it's going to be deployed. That's something I had to learn. But so yeah, I'm not for NR. I'm not sure actually if there would be any SIG study at the moment. But the most recent is the joint mapping I showed before.
Okay, thank you. And we also have one question related to this All right, so for this energy efficiency question from Amr, I guess Anup has already answered your question. So I believe once you read this paper, you will get much more understanding about the energy efficiency gain of rice splitting. So I will not go into deeper about this question. And we have another audience raise his hand. Hi, Mustafa.
Hello,
Sorry.
hi. Am I audible?
Yeah,
Yeah,
it's
thanks
available.
for your nice talk. I have a question about the hard quick and soft quick. Among these two approach, which one is more robust to imperfect SIC?
Okay, one sec, let me put the slide in. Okay, so which architectures you were saying, Mustafa? Sorry.
The hard quick, CWC, CWIC, and the soft one.
Yeah, so regarding hard quick and soft quick, soft quick here because you use the soft vim. So I think the key point here is that with the hard quick, we are removing the soft information from the LLRs.
True.
And that's with the soft quicks, I mean, though that soft information that gives more information then to the mapper to have a better LLR estimate. So using soft information is generally better for the performance.
Mhm. So it seems like it is more robust. I mean, if you have, for example, imperfection in SIC, then using soft is better.
I think so. I think so because you will have the information of the probability, and then it will be
True. True.
at least the LLR will give you a sense. Well, it would be maybe a smaller LLR, and then the information will be taken into account in the decode, LDPC decode or polar code.
True. True. Thanks a lot. Thank you.
Thank you.
Thank you. And we also have one question from Fajem. Considering RSMA, is it possible to harvest energy only from the common stream using power splitting, swept for sustainable 6G?
So I haven't done any work on power harvesting or anything. So I'm not. I don't know actually about that topic, so I'm not able to reply to that one. I know there are multiple papers, but I cannot say anymore.
Yeah, I think Fajem, you can go to search. There are many existing works on RSMA and swept, and I believe from the theoretical analysis and also simulation results, they have already shown that RSMA can utilize this common string to do energy harvesting. All right. Any other questions?
Lena, I have one question, if I may.
Oh, sure. Go ahead.
So, Dr. David, thank you very much for this nice talk. And I just had one question regarding the pre-standardization activities. By that, you mean more standardized test, as in the industry route where we go from MATLAB to test-bed simulations to field trials? Or are you talking about consensus building among the industry players? What is more important according to you?
Thank you, Anup. Well, I think all prototypes and trials, those are really important. What I actually meant was more industry consensus, to having different players across the value chain, MNOs, vendors, service providers, chip manufacturers, and to start having a discussion about potential gains, potential specification impact, and all those kind of things. There are activities. So there are activities for other technologies like RIS. So there is ETSI industry specification groups on RIS or terahertz or ISAC very recently. So we're starting as well to have discussions whether we could do the same for rate splitting, to have more, because to tell you our experience, we submitted this to 3GPP, but it's a very new topic. All companies have their agendas. It's very difficult to go through. So it's normally I think you need to work together with the companies, and then have a discussion for 6G, because we may find something, or there may be a new challenge we didn't discover. So the thing is this consensus that needs to be done.
Right. Yeah. Thank you very much for the answer. It was very enlightening.
Thank you.
Thank you, Anup. I guess Sundar also have some other questions.
Yeah, thank you, David, for this nice presentation. Just to follow up on my first question. I mean, it's entirely likely that a future release might say, just like this low complexity ML joint decoding receiver is standardized, you could have a scenario where SIC is also standardized, right? That's also possible. Could you comment?
Yeah, I mean, it could be, I mean, anything could be standardized. I mean, if there is enough companies providing support, evidence there is a gain, it could be, I mean, if, let's say, there's a study, or RSMA is studied, and then companies, the analysis show that actually a more SIG type of architecture is more beneficial, then that could be specified. I mean, in run forward, I think they specify is like the modulation requirements. I don't think it's the exact structure is specified, but it's kind of like you would need to do something similar to reach that performance requirement. But it could be. It's no, there is no impediment.
Okay, thank you.
Thank you, Sundar. Any other questions? All right, so actually I have one very general question. So because most of our audience are students, and I would like to ask a question from the research perspective. So whether, because as you mentioned that the time left for RSMA is actually limited, so for the next several years, and what are the most potential research directions that you think for RSMA in the coming several years, that maybe we can put our efforts on to help with this standardization? Yeah.
Yeah, well, that's a tough one. Yeah, I think, so, well, one, I mean, there has been a lot of work on RSMA on different directions. Give you just some thoughts out of my head. For instance, ISAC is going to be very prominent in 6G. I know there is work on RSMA with ISAC, how they could help. I think that's a very interesting topic. Then on evaluation as well, I think system level simulation could be quite interesting. I think it's something that is missing. To have, like, you have a network, and then you have multiple users in the network, and then you start dropping users, simulate how RSMA performs with under realistic channel modeling. I think that's also quite important. So we have done a lot of work on link level, but system level as well, I think, is something that we will need to work to show the gains in more realistic environments.
Thank you. Thank you, David. Yeah, these are actually two very interesting directions for us to work on. All right, so if there's no question, I will end the webinar today. But I would like to remind all of our audience about the two call for papers of RSMA. So there is one for the ICC 2024 workshop on RSMA, and also another special issue of RSMA in IEEE transactions on green communications and networking. So you can go to our webinar website and also our SIG website for more information. All right, thank you all for attending this talk, and as this is the last webinar for this season, so looking forward to seeing all of you in the next season of our webinar. And thank you, Debbie. Thank you all. Bye-bye.
Thank you very much. Thank you.
Thank you, Dr. Vargas. It was really enlightening. Thank you.
Thank you very much for all the help and organization. Thank you.
Thank you.
Thanks a
Bye-bye.
lot, David.
Thank
you, everyone.